So here I have a minuscule example of a parallel circuit. Each of the two loads are in parallel. It means they run parallel lines to each other. They run next to each other rather than in line or in a series. So I don't have light bulb after light bulb. Comparative to old Christmas tree lights to new Christmas tree lights. This version would be as if you had the new Christmas tree light style versus your old Christmas tree lights, where if you bulb blew out, none of your bulbs are working, and you're spending hours trying to figure out which bulb was bad. So here we have two lights that are working right now, and we want to measure voltage is in parallel. So I'm setting my meter to volts right now, and right now I have about, let's see, switch the leads back. I have 4.1 volts, which should be roughly 4.5, but I have two loads on the circuit. So I'm going to turn the circuits off. Back up to 4.3. I have 3 AA batteries, which are in a series, back to back, so each voltage is added up. Batteries, if they're in series, you double the voltage. If they're in parallel circuits, you double the amperage. So I have 3 batteries, AA batteries in series, with 1.5 each, making a 4.5 volt battery pack right here. Now across the two terminals of battery, I have 4.3 volts right now. As soon as I turn on my loads, they drop to 4.1. Now, and this is why we use, going back to the Christmas tree light example, I can remove this incandescent bulb here, and my LED still lights up, and vice versa. And I got a weak contact here. So if we lose a bulb, our circuit's still complete. If we lose both of these bulbs, we no longer have a completed circuit, and we have both of these loads would have to be bad or broken wire. As you see, I got a little bad contact right here. And of course, I included a switch. Switches aren't necessary for a completed circuit. It's just a quick on and off on our ground side. So if I want to check amperage of these two loads, I can remove part of the circuit. These blocks have conductors in them, so it allows us to make a quick example. And I'm going to put my meter to amps, and I can check the amperage across these two loads with it on. So the lights came on with my meter off. I'm completing the circuit, and I'm drawing roughly 15 down to 10 milliamps. But I mean, I have two small lights, but this is just an example of the loads, of how little power it takes to draw down a battery overnight. So this is just an example of how little amperage is drawn from just a couple of simple light sources. Now, if I wanted these sources in parallel series, I'm sure I'd draw a little bit more. So now I got these lights rearranged in a series. I'm going to see how many amps they draw together. So now I'm drawing about 4 milliamps. But if I watch the voltage, if I put this back together, I'm going to watch the voltage difference between the two. So the advantage to having the parallel circuit is our resistances are divided to each load, rather having all the resistances stacked up. Where if you have them all stacked up together, your loads, one of your loads or multiple of your loads, are possibly not going to work. So just to show you the resistance values of this particular incandescent bulb, suppose I should have my alligator's clamps on for this, are 7.6 ohms. So our LED resistance is going to be much more. I mean, it's built as a resistor diode. So we have 8.03 million ohms. So this is going to take up most of our load. I had this in the series earlier, and only the LED would light up, not the incandescent bulb. This takes up so much of the load, which surprisingly it's an LED, but because it has so much resistance in the circuit, the incandescent bulb would not light up. Now this Now the incandescent bulb just is one circuit wire thinner than the rest of the circuits, so it adds some kind of resistance. And it heats up and almost to the point where it burns had it had some kind of fuel to allow it to instead of inert gas. While these two were in series together, the incandescent bulb would not light up. It just acts as another connector because the LED, with such a big load on it, takes up most of the energy. So hopefully now you understand at least the loads, voltage, and amps part of it, even on a small scale level. I mean, your loads are really anything that's going to cause a good amount of resistance on the circuit, usually light bulbs, electric motors, radios, that kind of thing, headlights. So anything that's going to start using up amperage, even a relay can kind of be considered a load. It's a control side circuit. It's going to put a load, electromagnet activating a switch. So there's several different types of loads, and this is just a simple circuit using these blocks. Pretty nice example to set up and kind of play with too. And it helps basically understanding. And you can also have what's called a parallel series or series parallel circuits, where you have a light bulb in line with your main circuits, like in line with your switch. So you could have like a light bulb where the switch is, and then two other light bulbs right here in parallel. And that would be considered a parallel series. I don't have another load that I could put on this other than an electric motor, which starts to take up a little bit of room on the board. So now I have a parallel series circuit where I have a motor in series with both light bulbs, and the light bulbs are still parallel. So I'm going to go ahead and turn this on, and it's to the point where the motor is drawing up a lot of energy, and yet the light bulb, the incandescent bulb, and both, this time my LED is just barely lighting up. It's kind of dim down there at the bottom. Let me see if I can turn this other light off here. You can kind of just barely see the LED kind of glowing a little bit, flickering almost. That motor's humming away, but at a slow speed. Sometimes it's untelling which load's going to get used up first with series, and it's just literally coils of wire, so it's flowing through the motor and it actually causes it to spin. Well, this one is actually showing up now. The motors, we'll check the resistance on the motor quick just to see where we're at with that. So our motor only produces 3.9 ohms of resistance. So we're more than good there on our motor to light up both the incandescent. However, the motor is using up more energy than the light bulb this time, the LED. So the LED this time is barely getting lighting up, and it's kind of flickering while the motor is drawing more amperage.